let's talk about applications a little bit today. I have a note sheet for you that I'm going to be passing out. And again, I know that some of this will be familiar to you. So please help us along in this process. I know that some of you have done application problems in the past. And let's name a few. If you're a teacher of trigonometry, what are your favorite application problems for periodic motion? Ferris wheels. Yeah, Ferris wheels. We got to do a Ferris wheel problem. Radio waves. Yeah, sound waves. All right, everyone have a note sheet? All right, yeah, absolutely. We can rattle off a whole bunch. We're going to do the very first problem we're opening with is thanks, guys. The very first problem we're going to open with is a tide problem. It looks like at an average temperature problem. The last one on there is a pendulum problem. It's height above the ground being modeled by a sinusoidal motion. What else? Another favorite one is a spring-mounted weight bouncing up and down over time, creates periodic behavior. Or how about anything at all that's circular in motion, right? Recording the distance that a point is, like a Ferris wheel, exactly, away from a fixed object. We get sinusoidal behavior. Thanks for being quiet. All right, cool. And then anything that's a waveform of any kind too we might model. In your homework I think there's like a heartbeat problem, which is not perfectly sinusoidal, but it is perfectly periodic. What else? Like yeah, someone mentioned radio waves or anything on the electromagnetic spectrum altogether, right? Including light waves or sound waves. Anything in music you've thought about maybe?
Or temperature.
Average temperature is going to be on this one here over the course of a year. Yeah, and maybe even like economic phenomena, maybe, I don't know. All right, so there are lots of things that we can think about in life that are periodic. There's a season for everything, right? Turn. Okay. Who likes reading? Is that you? Yeah, no, go ahead. Wait, yeah, but in the voice of Javert, go.
All right. On January 1st, 2008, the first high tide in Ocean City, Maryland occurred at 2:11 a.m. At that time, the depth of the water was 1.9 meters. The first low tide occurred at 8:14 a.m. at a depth of 0.4 meters.
Excuse me, I shouldn't make you say it, is what I should do.
Yeah.
That's true. He doesn't really talk, he just sings. Everyone should go see the play again tonight. Quick walk. Or go see the hockey. All right. Good. There's so many exciting things. There are really two pieces of information given here that are going to help us plot this. You don't have a picture of this on your paper. I have a nice grid that's going to help me, so sorry. Okay, it's all good. Actually, sometimes the grid gets in the way of life too, so maybe you're better without the grid. There are 2 points given that I'm going to plot right now, okay? Now, before we go and plot points, we should kind of think about what is the dependent and what's the independent variable. The independent variable along what would normally be the x-axis, we're going to consider that to be time. Is that okay? We're going to have to still think about that some more. And we want to model over time what the depth of the water is off the bottom of the ocean floor, I guess, at the particular point we're measuring. Sure, okay. And, all right, we're still not done making choices. Depth is going to be in meters, so a depth of 0 meters is associated with the water there not being any water, and, maybe I don't know if that'll happen at all. What about time? That's maybe the trickier one. What do we want to say about time? The very first time is 2:11 a.m. So we could associate that with the time 0, but that's kind of messy because then after that, it's not real nice. So let's associate like a nice time with t equals 0. We could associate 2 as t equals 0, or you could even be nicer and associate midnight with it. Then like every t value corresponds to like the actual time on the clock too. That's nice, but do what you like, okay? In the end, we should all get the same answers if we cross our t's in the right way. Okay. So conveniently, I have a grid that has 24 marks on it here. Conveniently. Okay. So you should scale yours maybe over the course of 24 hours too, just so we have a whole day's activity. Mainly because I've looked ahead and I already know that like 6 a.m. I care about 6 hours after midnight, but I also care about 1 p.m., which is even more than 12 hours after midnight. So we're gonna want maybe 24 hours of activity. Sounds like a good idea. 1, 2, 3, 4, 5, 6, 7, 8, 12, 6. All right, we're doing well. I'm gonna scale the D axis here. 1, 2, 3. How about call that 1 and call this 2, 4. How about call that 2? All right. Whew, I think I'm ready. All right. So it says the first high tide occurs at 2:11 a.m. and that tide is measured to have a depth of 1.9 meters. Okay. So the first thing I might do on my calculator is I might say, all right, well, 2:11. I'm not plotting the point 2.11. Comma 1.9, right? It's not 2.11 hours. Yeah, it's 2 plus 11/60ths of an hour, isn't it? Isn't that what that really means? So, and I'm gonna maybe just in case I need that later, I'll store that in A. Okay. So the actual amount of hours since midnight is 2.18. It turns out approximately, but I have the full stored value. So 2.18. So here it is. 2.18, comma 1.9. Let's call that, oh, I don't know, how about there? 2.18, comma 1.9. Perfect. All right, the next piece of data that we were given is that we have at a low tide, the very first low tide occurs at 8:14. So 8 plus 14/60ths of an hour. This should feel familiar. I mean, when we were doing degrees and minutes, and, it's the same thing. Time works the same way. So I'll store that in B just in case I need B later. That'd be fun. 8.23 approximately hours is what that really means. 8.23. So that's around there. How about 8.23 comma 0.4? There's 0.5. How about there? I don't know. Just eyeball it. 8.23 comma 0.4. Okay. And then I claim that actually that's not very much information, but I kind of have everything I need now. Even though I just have 2 points, I think I'm good. Okay. So if this really is the first high tide and this is the very first low tide, there's not anything happening in between. There's not like another high tide before or another low tide before either of these 2 points. We have the very first two. And assuming this behavior is sinusoidal and continues in like a perfectly nice continuous manner, which is actually an assumption that's not very far at all from the truth. It is almost perfectly sinusoidal. It's not totally perfect, but it's pretty close. All right, so I think the graph already, I'm thinking, the graph looks something like this. I think I already have a feel for it a little bit. So let's ignore questions A and B completely right now and just see if we can come up with a model that goes through these 2 points, a sinusoidal model of some kind. And of course, by sinusoidal, I mean could be sine or cosine when we write it out. There are a couple things we can definitely agree on, like right away. We have a maximum. It seems like if this is the high tide, then at least for, the sake of discussion, all the high tides and low tides will occur at this place. All right? So, can you tell me what what do you want to start with? Can someone give me a sinusoidal axis or the amplitude, and how, I guess more importantly, how do you find those? Let's start with those two. So which one are you giving me, Isabella? Tell me. How do you get it, though? 1.9 plus 1.4 over 2. Why does that work, and what are you doing? It's the halfway. So we're looking for the sinusoidal axis, which is like the halfway point between those. So use any kind of argument you can in your own head. There's no formula for you to memorize, even though you could memorize that, I guess. But, right, just think about it. It's halfway between. So, like, eyeball it and think about it. Or this is the average of those two values. You could think about it that way. It's the average.
Subtract one from the other. Divide by 2 and then add that to the lowest.
There you go. Yeah, absolutely. A couple different ways to do it. That brings us to the amplitude, actually, which you've already kind of computed in your way of doing it. Justin, how do you find the amplitude?
You subtract. But 1.9
Yeah.
from 0.4.
Yeah, find the distance between the total distance of this wave, of this waveform here, and then
And then you add it to the lowest.
To get the sinusoidal
Oh,
axis, you mean?
yeah.
Yeah, so the total distance from low point to high point is actually twice the amplitude, isn't it? So I think that'll give it to us. Anyone already do that? What is it? Come out. 0.75. And if you hadn't already done the sinusoidal axis, you could do what Justin said, and you could add 0.75 or to 0.4, or you could subtract 0.75 from 1.9 and you get the sinusoidal axis. Or you could, if you have the sinusoidal axis already and you wanted to know what the amplitude was, you could do 1.9 minus 1.15 to get points. There's a couple different ways to do it. That's why I said I don't want to hand you a formula. You do whatever you want to do, just get the example. Think about the geometry of the situation. Okay, so maybe I'll plot that too. 1.15 is, I don't know, how about there? 1.15, these numbers are not perfect, but oh well, we got a general idea. What else do we like? How about the period? I think I'm ready to think about the period. Are you? Let's hear from someone else I haven't talked to today. Someone talk to me about the period. Who haven't I heard from? Please go ahead. Say something. Okay, I think I feel that. Yeah, all right. So did you catch all that?
No.
Say it one more time for Justin.
So from the first x point to the second x point is half of a period because it's the 12th point.
So it's half a period. Okay.
Then just multiply that by 2. And then you get the whole period.
All right, so where's my calculator? How do I get it? Okay.
Oh, so we're saying
So actually, I already have these values stored in my calculator, the x values, or excuse me, the t values, right? A and b, I already have them on the calculator. So I think what Lisa's saying is let's do b minus a, this value minus this value, and 6.05 is half of the period. The whole period is 12.1, right? So we just figured out what the period was through a process I'm not writing down, sorry. It's 12.1. Okay? Beautiful, beautiful. That tells us what the period is, but eventually our goal is maybe to write, in a second here, I'm going to write an equation. And in that equation, I'd like to know actually not maybe the period, but what the actual b value is. So you already had to have thought about this today for that warm-up you did. Talk to me about b. I know, because I've been paying attention to Mr. Chage's lessons that the period is equal to 2 pi over b, but I was never given a formula for b if I know the period. So b is equal to what?
2 pi over period.
Oh, it's the same thing basically. Oh, that's kind of convenient. Okay, good. If you solve it for b, that is in fact what you get. That's pretty cool. So what's b? 12.1 is the period. That makes b 2 pi over 12.1, or pi over 6.05. That's a number I've already seen today. Okay, beautiful. So I'm ready to write this out here. It's 0.75 times, well, I haven't figured out which function I want, but it'll be something, either a cosine or a sine of b, which is pi over 6.05, times t, maybe there's a phase shift, I don't know, I haven't thought about it yet, plus 1.15. All right, so now we need to make a decision about whether we want to use a sine or a cosine. So someone talk to me about what would you like to do. You're welcome to use either one, but being mathematicians and wanting to be as lazy as possible, why is cosine a good choice? Yeah?
Because it's more of a, little thing.
It's more of a little thing.
Like,
Crystal clear now. Thank you, Justin. Yeah, no, I think I know what you're talking about. Yeah. Yeah, because the information is given is in terms of maximums and minimums, and we're already thinking about what the phase shift needs to be, right? So that's pretty great. There's no reason you couldn't calculate what this point is right here, this halfway point in between these two, where we're at equilibrium, or this point over here, which is the next point it'll reach the equilibrium, the sinusoidal axis. But again, why bother? We're lazy, okay? Let's go with what we want and what we feel like. So I think cosine's a good choice, and it will be actually for a lot of these modeling problems, because what we know is like maximum and minimum information. So a lot of times we're reaching for a cosine model. All right? There's no rule about that, and you can use a sine if you want. All right, so if that's your choice for cosine, then if that's your choice, then what do you want to make the phase shift? We're finally ready to write this down. What's the phase shift? Yeah, 2.18, right? And by 2.18, I mean, let's use that stored value in the calculator. All right, so with that in mind, let me just make sure, that's the reason I waited on doing that last, is because no matter what your model is, no matter what my model is, no matter what your friend's model is, these three things here that we first calculated should everyone in the world will agree on, right? Everyone's model will have those three things true. But then you have to make this choice about, do you want sine or cosine? What's the phase shift going to be? Now we have a discussion, right? But I think this is probably the most natural model that all of us came up with, so we'll go with it. It's not the only one that's right. But
Should be in 3 sig figs when you do the phase shift.
when we do it on the calculator, we're going to pull in the full value. And I think we're ready to do that now.
Oh, we're going to do it on the
So here's the calculator. I'm going to try and enter this into the calculator here now. In y equals 0.75 cosine of pi over 6.05. That was exact, so we're not rounding. There's no rounded value at all in this equation. X minus, what's 2.18? Oh yeah, that's right. It's a in my calculator. Plus 1.15. All right. How do you like that? Now before you go and hit graph, don't do that yet. Hit window and set up your window. And actually I've already done it from my last class here. 0 to 24 on the x-axis. I'm just going to make it look exactly like the thing I have up on the screen here. And on the y-axis, how about 0 to 2, right? And then are you ready to watch this thing happen like magic? Oh wait, hold on. One more thing before you press graph. We got to keep giving you a little cliffhanger here. Is your calculator in what mode should it be in? And does it matter? All right, the way we've written the equation, I think the answer is maybe radian. But what if your calculator's in degree mode? How about this? Instead of changing the mode, could you change the equation so that, how would you have to change the equation, Pat? I mean, I would type something different into y1. Like it would be an actually different equation. Because mine's in radians. Natalie?
Instead of dividing 2 pi to the period into pi b, divide b 360.
Yeah, exactly, right? So this pi, instead of pi, we might put a 180 right there. And then it would be fine. If you're in degree mode and you put a 180 there instead of pi, that will work just wonderfully.
Wait, wouldn't the phase shift have to be different though also?
And the phase shift would have to be, no, I think we're okay. Try it and tell me how it goes, all right? Put it in degree mode, and I think the only change you'll have to make is 180, and you have to think maybe about that, Dale, why I'm right that nothing else has to be done. Okay, all right, here we go. Oh, we'd have to actually graph it. This is the fun part. Did we do it? All right, that looks like 2:11 a.m. to me. That looks like 8:14 to me. All right, good. Yeah, this looks good. Looks good. Looks good. Let's actually trace and see. If you trace, if we trace to, how about if we type in alpha A? Look at this, right? Blink, blink, blink at 1.9. If we type in alpha B, blink, 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 0.4. Perfect. That's exactly what we wanted. It seems like our model does, in fact, do what we want. Go through those 2 points we care about. What's that? We don't know what the y-intercept is. Who knows? No one knows. All right. So we can actually draw this here, right? If we want. I'll just be rough about it. There it is. Something like that. Okay. That's not very good, but we'll go with it. We didn't actually answer the questions yet. So tell me, when is the water level at 6? What is the water level at 6 a.m.? What is the water level at 6 a.m.? How do I figure that out?
Plug it in 6.
Yeah, it's right in front of me. Put in 6.
It's
0.850. Write that down. I'm not going to write it down up there. You can. 0.850 is the answer to part A for 6 a.m. What about 1 p.m.? I just have to type in 1, right?
13.
Oh yeah, 13 is what I meant by that, right? 1 p.m.
Did you do that part on purpose?
1.74 is what I'm getting on the calculator. You can do it too. You can write that down if you like. So those are your answers for A. And then your answers for B, your answer for B is a little trickier. What does it say? What is the first time when the water is 1 meter deep? How do we do that?
Just do it in y equals.
Yeah. Put 1 in here. You've done this before. There's a line that shows us the depth of the water being 1 meter. And we'd like to figure out where that point is there. The first time, it's critical here that the problem must say, the first time that it is at the height of 1 meter, right? Because there are lots of times when it's at a height of 1 meter. And now when we find the intersection on our calculator, number 5, the guess piece of this, if you haven't had this experience before, the guess piece is actually somewhat critical here, isn't it? I mean, we can't just assume we know which intersection you're talking about. We need the first one to say, I guess. That's what the problem says. So anyway, the point is it's 5.596 whatever. What time is that, though? All right, here's a calculator life hack trick. Are you ready? Go back to your home screen. Hopefully you haven't done anything else on your graph. The very last thing you did on your calculator was to find the intersection, right? So the very last thing that is stored in the value x right now is, are you ready for it? 5.596, etc. Mind blown, I know, right? So that value is critical because we'd like to know what time that is. It's 5.596 hours. If we subtract 5, then that's the number of minutes. Let's convert that to hours. So it's at 5 a.m. and 35 minutes, and hey, you want to be even cooler? 35 minutes and 46 seconds approximately, right? So we could actually convert it that way. What did we say? 5, 35, and 36 seconds, just to be really cool. Okay. But you see what I'm saying? Or you could say like, you could say around 5:36 or something. I don't know.
Why can't we do that?
We okay? Pretty tricky stuff, yeah.
Degrees, minutes, seconds could be done with just the first number not being a degree, right? Or is it?
I mean, doing that whole process I just did is the process you've done before with converting degrees to degrees, minutes, seconds, for example. You've done this before. And you've maybe done this before exactly, doing with times, right? You know? Someone says like, what's 5.5 hours from now? 5.5 hours from now. You're like, you mean 5 hours and 30 minutes from now? You just did that conversion without actually even thinking about it, right? All right, stay with me. All right, we had like a really deep and really extensive conversation about the first one, but we're gonna have a pretty limited and quick conversation about this one and maybe even the third one. We'll see if we get to it. All right, so the next one here, someone got a good Scottish accent out there?
Right here.
Come on, where's my Scottish? You want me to? You want me to? I don't know how I can do that. The average monthly temperatures from October 2007 to October 2008 for Scotland. Is that too much Irish? Are shown in the table below. Give a sinusoidal model using 31 as the minimum and 66 as the maximum. That's the best I can do.
Giant, like, military vibe.
All right, that's the best I can do. Sorry. All right.
Arnold Schwarzenegger.
Hold up. So now we got a whole bunch of data, and it's not perfect, maybe, and maybe our sinusoidal model won't go through all the points, and that's just okay. Now, some of you might be an instant reaction. You're like, I know, because I'm a calculator expert, that there's like a sinusoidal regression feature. So if you're that nerdy person, please do that for us off to the side and tell us how we do. Because we're just gonna eyeball it, okay? We're just gonna go with like a really crude model. And for that, all I need is 2 points. I just demonstrated that in the last example. Can you find me a max and a min, maybe? How about that guy is a minimum, looks like to me. We go down and then back up. And how about down here? So with those 2 points only, I'm going to write my model. And we'll see how my model compares to your model. We'll graph them side by side or something if you want. All right, so again, I'm going to think about what the amplitude is, what the sinusoidal axis is, and what the period is, etc. All right, so what's the amplitude? Let's start with whichever one you like here. What do you got? Like this sinusoidal axis? Amplitude, you want to do that one first?
Sure.
Go ahead.
The amplitude would be 66 minus 31 by 2, so that's 60. 66 minus 31 is 32.
Can someone confirm that?
How would that math work?
16.5? 17.5. She's correcting you, but your process is right. That's what counts. Good job. 17.5, do you agree? And the sinusoidal axis is something. What is that? We're getting good at this now. Sinusoidal axis is the halfway point between those, and what is it? 40 something?
48.5.
48.5. See how quick we're going through this now? What's the period? That's from a min to a max, and t is measured in months. So, talk to me.
66 minus
Even before I showed you the data, you might have guessed that the period was
7 years.
what is it?
A year.
Yeah, 12 months, isn't it? Isn't that the period? Okay. A year. So that means b is equal to 2 pi over 12, or how about pi over 6? All right, so we're ready to write our model here. How about we'll call it big T of little t. 17.5 times, I think we're ready to use a cosine again, right?
Yeah.
Pi over 6 times t minus, I haven't thought about it yet, plus 48.5. All right, we're doing well. Stay with me. What do you want to do with the phase shift here? We haven't discussed it yet because everything else was for sure. This is the part that we might have like a conversation about. What would you like to do? You want to shift to where?
Right one.
We want to shift to a max or a min if we've already decided on cosine. So
3.
you want to shift here?
Yeah.
Okay, that's fine with me. But then of course that's a minimum, so we'd have to throw a negative out front. So that's perfectly fine. Full credit for that answer. Alternatively, you could have given the model 17.5 cosine of pi over 6 and how we're going to shift here.
And then t plus t minus 9.
T minus 9, or 9 months. 9 months from now. 9 months from now is the same as 3 months ago, right?
So we could have done that, yeah.
Any of those three would be perfectly fine, right? So graph mine too, and see how they compare. No, the last one is shifting to here, which is a maximum. 3 months ago was a maximum too. Right? So all of these are correct. Any one of those is a good one. All right, we didn't have time to get to the last one, which is not a problem. It's a pendulum problem. You can do that like on the bus today, or with your friends at practice. During the, whatever, something. I do have some sad news for you. I will not be here next week.
Oh, that's
For the entire week.
2.5 days
I know.
next week.
I'm going to flying out to California to visit with my wife's family, and
Oh, they're saying visit with
you
your
can
wife.
email me. I have a math job. Pretty close, huh? Pretty close. Yeah, right? I love you all. Bye. I think it ends on Monday. What did you say? Yeah, I don't even know. When does this thing end? I don't know. Do you know? You should know these answers. Deck of people. So did I.